Okay, let me start the last class of the week with a problem of projectile motion. So if you remember, we went through this yesterday, and I would like to solve this problem before we jump into the next topic. We're still in dimensional motion. So today we're gonna take a look at circular motion. But first, let's take a look at this projectile motion problem. So if you just wanna move to section 4, problem 1, I'm gonna read the problem. So it says, a man throws a stone at 20 meters per second at an angle of 45 degrees. And it asks, how long does it take to reach the maximum height? What is the maximum height? And then you get to construct the graphs corresponding to the position, velocity, and acceleration of the stone as a function of time. So let's just refresh a bit what we have here. So for starters, we can draw a system of reference that will look like this. Let's say we have y here, x here, origin, and then our stone starts with an initial velocity v0 with an angle, and that angle is alpha equal 45 degrees. So in order to calculate the maximum height, we would need to write our motion, our equations of the equations that are governing the motion, right? So if you remember, we had a straight line motion, a uniform straight line motion on the x axis and a variable straight line motion on the y. So we have acceleration here, and the acceleration would be g, right? Pointing down. The gravitational acceleration. So we can project Vy and Vx into each of the axes. Let me just move this a bit so we can have a better view. This here is alpha 45 degrees. So we can project the vector into the axis, and we can calculate the components of that vector. So we will have both coordinates, Vx and Vy. And now we know that these two V, X and Y are the ones that are affecting each of the decoupled movements that we have in each of the axes. So we have a straight line with no acceleration on X, and we have a straight line with G acceleration, and that will be basically a free fall, right? So we know the trajectory of this thing will be something like this, a parabola. And let me make this a bit longer so it's more consistent. There, X will be a parabola. And the problem is asking the maximum, let me use someone call the maximum height, let's call it H, for that for the movement. And how long does it take to get there? Okay, so if we start getting some calculations, we know that V0 is 20 meters per second. That's the speed, that's the modulus of the velocity vector, the initial velocity. So we can say that the vector is composed of, we can express it through the components. So we have 20 multiplied by the cosine 45 degrees vector I. So remember, unity vector would be here, and j would be here. Plus 20 sine 45 degrees vector j meters per second. So these two components that we have here are the x and vy. Then we can write our acceleration, our vector, that would be 0 I minus 9.8 j meters per second square, because we have no acceleration on the x-axis, but we have g, and now remember g is pointing down, so it's going the other way. It has the opposite direction of the y-axis, so we have this minus in our component, right? It's a negative component for the acceleration on the y-axis. Okay. Then what we can do is write this vy of t, right? So the evolution of the velocity in the y-axis over time. And that will let us know at what time we get a highest point, right? Because at the highest point, the velocity in the y component would be 0. Is that clear? That's the condition that we're looking for, because it's asking how long does it take to reach the maximum height. So the maximum height will happen when the velocity, when the vertical component of the velocity equals 0. It won't keep going up. It will start accelerating down. So if we write vy of t, this will be v0 y minus gt. So remember, initial velocity, acceleration times t. That's the equation we need to express the variation of velocity over time. And okay, again, the minus sign comes from having g pointing down, which is opposite to the y-axis pointing up. So we can replace the values there, and we can say, okay, we want t, so that vy is 0. So let's say vy equals 0 equals 20. Let me get the zeros there. 20 sine of 45 minus 9.8 meters per second times t. Okay, so we can get t from that, and we can call it t max, let's say, for maximum height. So t max would be 20 meters per second cosine of 45. Remember, well, cosine of 45 is the square root of 2 divided by 2. And all this divided by 9.8 meters per second square. And that's 1.44 seconds. Again, dimensional analysis, we get rid of the m's, we get rid of the s, the square, and we end up with seconds. So this checks. So we have 1.44 seconds. That's the time it takes for the stone to get to velocity 0 on the y-axis. And that means that it's on the highest point, right? So we have that time here, time to reach H maximum. But we don't know H maximum, right? So what we need to do now is calculate the actual position of the particle at that time, because we know the time that we want to know where the particle is. So for that, we can write the equations, both equations of the movement. So we have xt. Remember, we don't have acceleration there, so it's just x0 plus v0x multiplied by t. And for the y-axis, we have y0 plus v0y t minus 1/2 of gt squared. So those are the two equations that will rule our motion in both axes. But what we need here is to know the maximum height. So we can call Imax equals, it will be equal to y at time 1.44 seconds, because we know that that's when velocity becomes 0. The y component of velocity becomes 0. So we can replace the values in the equation for the y. So we have y0, that's 0 because it's starting from the bottom. It's from our floor of reference, let's call it. So we have 0 meters plus 20, the component, right? V0y, which is 20, the sine of 45, which is 20 meters per second multiplied by root square of 2 divided by 2. And we have 1.44 seconds, which is the time that we're replacing, substituting the equation, minus 1/2 9.8 meters per second squared, 1.44 seconds squared. So we're replacing time here, 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 here. And these terms, let me highlight those. Yellow here, G here, and that Y is there. Okay. And now we simply calculate that, do the math, get the numbers in the calculator, and you get max, Y max 10.2 meters. And that's the answer to the problem. Okay. I think those are the two questions. How long does it take to reach the maximum height? Yeah. What is the maximum height? That's it. Okay. Something that is not asked here, but we can actually calculate it, would be the reach of that movement. So we can calculate, we can calculate this point here. So that will be x of one of t, right? So, oops. So we know this thing will be symmetric. So the time it took to go up will be the same time it takes to go down. If not, you can do, if you don't believe me, you can do the calculations from Vy0 at that high, and it will give you the same time because it's a symmetrical, a mirrored trajectory. So we could calculate that, and in some problems, it will ask you that, the reach of that movement. So that will be as simple as doing x2 by t max in this case, and that will give us x, let's call reach. Okay, just to comment on that, because you'll see that question coming in this kind of problems. When we plug, let me open the question, sorry. So Nathan, yeah, Nathan is asking, when we plug in G 9.8, how can we be sure G isn't negative? Isn't it going opposite to our velocity vector? Well, yeah, it's negative. You see, so we have negative, negative, negative here. It's always pointing the other way. Or you mean when it's when it's coming down after reaching top high? Well, the actual equation is it's with a plus, right? So if you just write the general equation of displacement with acceleration, you'll have this plus v0t plus 1/2 of acceleration t squared. But now our acceleration is minus g, so that plus will turn into a minus. Yeah, okay, awesome. Okay, any other questions about this? Is it clear? Okay, so let's construct the graphs that they're asking for. It says construct the graphs corresponding to the position, velocity, and acceleration of a stone. So this is it's not strictly, graphicking with, with scale and all that. It's just an idea of what it's going on with the movement. So if we just start from, we love this thing to make straight lines. Okay, so we have x meters, we have t in seconds, and let's graph that. So we have on the x-axis, we know, as we said before, we don't have any acceleration. We have just a constant straight line motion with some initial velocity that would be the component, the x component of the initial velocity vector. So we just have a straight line coming up. And if we want to put some numbers to this, we know that the thing will do 2t max, that's 2.88, and it will reach, x max, let's call it x max, not x reach, it's kind of confusing. X max here, just to have an idea of how do we graph that. So it's just a straight line. We don't have any acceleration. The slope of that, it's the initial component of the the x component of the initial velocity. Then we can graph. Go. Then we can graph t seconds here and y in meters. So remember, this is the variation of the particle with time in each of the components of the movement. Yeah, so this is not the trajectory. Again, the trajectory, we draw it up here. This is what it says when you need to graph the position. So the position here is composed by two separate movements that then we couple them. So we need to graph x of t and y of t. And y of t, as we saw before, well, up here, it's a parabola, right? So we can approximate a drawing of a parabola. We know this is 0. We know that that gets to the top point at 1.44. And this is 2.88 seconds. We calculate the maximum height, which was 10.2 up here. And that's basically it. That's the variation of the position on the y-axis. Okay, let's draw the other ones. Velocity. So for velocity, again, we would need to graph both components. So we have time and we have Vx in this case. Oh, sorry, units Vx, that would be meters per second. And we know that at Vx, we just have a constant speed. So now you can do 2.88. That's the maximum of the whole movement. And that will be 20 multiplied by the cosine of 45, which is square root of 2 divided by 2. Okay. Now let's move on to Vy. We have t seconds again. Vy meters per second. And for that, we can start from 20 cosine sine of 45, which is the starting point of our velocity in the y-axis. And in this case, we know that the stone will go up, decelerating at a rate of g, and then it will go down, accelerating at a rate of g after crossing the 0 point. So at some point, it would need to cross the horizontal axis, right? So this would look something like this. And that crossing point will be 1 or 24 seconds, because that's when it reaches the maximum height. And the last here would be 2.88 seconds, which is the whole duration of the movement. And that point here would be minus 20 square root of 2 divided by 2. So you can see the symmetry of the movement. Is that clear? So this portion of the movement is when it goes up, and this portion of the movement, it goes down. Note that the velocity in the y-axis, it's the same in modulus, but opposite in sign when it reaches the ground, because it's accelerating from the from the same, it's getting the same displacement, but from a different direction with the same acceleration in modulus. Okay. And acceleration, the graphs for acceleration are fairly straightforward, fairly trivial, let's say, because we know we have 10 seconds, AX meters per second square. So we know AX is simply 0, right? I'm just using another color so it doesn't mix with that. Oh, sorry, it's let me do it smaller actually, because we don't need that much space. So we have this TS seconds 9.8 because it's negative. Let's do the Y there. So this thing is constant at 9.8 through the whole movement. That's for the Y axis. And for the X, it's even simpler than it is 0. Okay. Any questions about that? There's well, yeah, it's kind of far. Those are the graphs that the problem is asking. So position, we have the two components, X and Y. Velocity, we have the two components, X and Y, and then acceleration. All of them as a function of time. Okay. Any questions? If not, I'm gonna move to the PowerPoint and we can continue with the theory. Okay, let me change this. Okay. We've been through this yesterday. Let me get to the next slide. All right. So we stopped here yesterday, and so these are basically the equations that we just applied in our projectile motion problem that we just solved. So let me just move to a new topic. Well, not strictly new, but it's a different kind of motion, which is circular motion. So if you remember, we strictly need some kind of acceleration to change the oh. Yeah. Can you just give me a thumbs up if you hear me right? Because I'm not getting the. Okay, awesome. Thank you, Anthony. Okay, so we have a uniform circular motion. So basically, we've seen that we need some kind of acceleration to turn the velocity vector in some ways. So in order to be able to change the trajectory of the particle. So let's define the uniform circular motion. So that's basically when the particle moves in a circle with constant speed. Meaning that the modulus of the velocity is gonna be constant, not the vector. Remember that we made that distinction yesterday. So speed is the actual value that the velocity has, the modulus of the vector. So the modulus is constant. The value of the velocity is not changing, but the direction is changing. So the vector is not constant at all, and that's a good question, right? That's a conceptual thing, right? So the vector is changing actually, because if not, we wouldn't have a change in the trajectory. So let's just think about a circle, and let's just think about the angle that the position vector will be sweeping while the particle is moving through that. It's moving following that trajectory, circular trajectory. So let's say we start here and we go up here. The angle that's being spanned by that vector will be 90, right? 90 degrees. If we continue, 180, and so on. If we do the whole turn, it would be 360. Okay, so that will be 2 pi radians, which is 360 degrees. So this angle we can measure it by using radians. So we can define the angular velocity, which would be the rate at which angle is changing over time. So that angular velocity, we will call it omega, and that omega would be expressed in radians per seconds. Okay. Sometimes you can, well, not sometimes, more often than not, you can see this expression RPM, that's revolutions per minute, and that would mean a revolution is a turns. So that would be the number of turns that the particle is performing in 1 minute. So that's another way of giving you the angular velocity. So that will be easy to translate to radians. Okay, so we defined this omega by the variation of the angle that's being spanned in that motion over the time it takes to do it. So you can easily see that it directly relates with any kind of velocity definition that we've checked before. It's basically a displacement over time, but in this case, displacement is an angle because it's following the particle on a circle. So the total time that the particle takes to make the complete turn, it's called a period. So if this thing is turning at a constant speed, it will have a certain period. So we can define that, and the frequency would be the reciprocal of that period. So it's 1/t. So that would mean that we get whatever number of turns per second, and that's frequency. And period would be the time it takes to make a turn. So we can redefine our omega as 2 pi times the frequency. Remember, 2 pi, that's the full turn, so times the frequency, the number of turns per second, then we have the angular velocity. And we'll get back to angular velocity in the next chapters, but now let's keep it this way. Basically, for us, for now, would be a scalar magnitude, although it's a vector, but we will see that further in the course. All right, let me move forward. So again, here we can take a graph and start looking at the magnitudes that we have for the movement. So we have R, which would be, in this case, the radius of our circle, and we have two positions of that of the particle in that trajectory, P1 and P2. So we already know that delta S would be that displacement, So we can do displacement divided by r to get this here. So we can get an expression for delta v equal to v1 divided by r times delta s. So again, this is basically applying vector algebra, some geometry here. So we can do you know, when you have similar triangles. So this triangle here is similar to the triangle that it's formed by the delta v. So subtracting v2 with v1, subtracting v1 to v2 actually. So this, when you have similar triangles, they have the same ratio for the sides and the angle. So you can see that the angle, it's delta phi here. So the similarity lets us propose this, that delta v over v1, which is delta v over v1 here, equals delta s over r. You can see that delta s would correspond to delta v and r would correspond to v1 here. Okay, so again, this is for uniform circular motion. So we're talking about constant speed. So the magnitudes of v1 and v2 are the same. So we can state that this triangle is similar to this other triangle up here. So if we work a little bit with that, we can then rewrite our average acceleration. That would be the delta velocity over time, over delta t, and then we can substitute this expression here that we just calculated for delta v, and that would get us v1 multiplied by delta s over r multiplied by delta t. And now what we can do is we can think, as before, that our delta t is very, very small, is infinitely small, and in that case we can take the limit. So when we take the limit, we arrive to this expression here, because we know that this delta s over delta t when t goes to 0, when delta t goes to 0, gives us the instant velocity, instantaneous velocity. So we will have v squared, this instantaneous velocity, over r. And that's what we call radial acceleration. That acceleration will be on the normal axis, which is in the same which is parallel and in the same axis of the radius of the circle. Yeah, so the instantaneous acceleration in this uniform circular motion will always point to the center of the circle. Okay, that's how we get that. And if we want to write v in terms of omega that we just seen before, we can rewrite this as the radius r time multiplied by delta phi over delta t, and that will give us r omega. Okay, this should be a cap r. This is the radius. Any questions about that? So take away from the main idea of this slide, we get some radial acceleration, which is affecting the direction of the vector v, because remember, the magnitude is remaining constant. This is uniform circular motion. So this v is constant in value in modulus, but it's not constant in direction. It's changing at each point of the trajectory. It's changing, and it's changing due to the acceleration, which is called radial, and it's pointing to the center. we will then define it as the centripetal acceleration, but let's call it radial now because it's on the radial axis. It's basically superimposed to the radius of the circle, and it's always pointing to the center. Are we good? Okay, let's move on. So, as I said before, basically, we have the acceleration that always points to the center, and we can call it centripetal acceleration. It's the acceleration responsible for changing the velocity vector's direction. So, as we mentioned before, the period t is the time is the time that it takes to make a full turn, so 1 revolution. So we can redefine the instant the instant velocity, and which is just the velocity because it's constant, the modulus, as 2pr divided by the period t. 2pr, if you remember, it's the perimeter of the circle, so it's basically the distance the particle is covering over that turn. So if we do distance over time, that's velocity, right? And then we can replace this, we can substitute this velocity expression in the centripetal acceleration expression that we got from before, v squared over r. So v squared over r would give us 4 pi squared times r divided by t squared. So we can calculate the radial acceleration in terms of the period and the radius of the circle. Okay. If you have any questions, please speak up, because this is it's a simple topic, but sometimes students find it difficult and unnecessarily complicated. So it's not. It's just application. It's just an application of what we've already seen. It's not something that is detached from the whole ensemble of equations and reasonings that we applied before. So if we have circular uniform circular motion, of course we can have non-uniform circular motion, and non-uniform would mean that now the speed can vary, so the motion is not uniform, just like the straight line, right? So we had a straight line with constant acceleration, a straight line with not even acceleration at all. So but in the circular motion, of course, we always need some kind of acceleration. So if we just have centripetal acceleration, the velocity the speed will remain constant, but the velocity not. The vector will change direction. And now if we have acceleration, some acceleration that is not only on the radial axis, then we will have a component of that acceleration on the parallel axis, or the tangential axis, if you want. Let's keep it the way the book defines it. So it's tangential. So the radial acceleration component will be still v squared divided by r, but then we would have a tangential acceleration that is parallel to the instantaneous velocity. So if we take a look at the graph here, let's see, we have some acceleration, which is not on the radius axis, it's somewhere else. So we have an angle there, and it will have two components now. It will have a component which is projected into the radial axis, and a component that is projected into the tangential axis, to the tangent axis. So that would be the parallel component that's pointing in the same direction that the velocity, that the particle is moving at that instant. Okay. So let's see how can we write that. Let's see. Yes. Okay. Yeah. Let's. Yeah. I'm not going forward with this. So yeah, we can keep it there. I think I'll skip the problem. We can take a look at the problem and well, let's finish the PowerPoint and we can take a look at the problem the last 10 minutes, yeah, because we have a couple of minutes. Yeah, so we're fine. Okay, so as I said before, if this thing has an acceleration which is not strictly on the radial axis, it will have a component into the tangential axis and the radial axis. And of course, we know how to calculate that. And that would be basically projecting that into both axes. So just remember that in this case, the velocity will change in direction and in modulus. So it will get in this particular case. So we have acceleration pointing to the same direction of velocity. Then as the particle moves, we will have a bigger modulus for the velocity. Then acceleration the projection will be smaller. And in this case, in both extremes, we can see that the full component of the acceleration is radial. So now let's say this acceleration is pointing against, it's pointing to the right of the radial axis, then it will have a component which is going in the opposite direction of the velocity. So we can say that the velocity will start decreasing as the particle moves until it reaches this point here. So this is just an illustration of what happens to the velocity vector in each one of the points and how that acceleration component will be changing the movement in each of the points. Okay, so let me, well, yeah, this is kind of a joke for physicists. So we have the steering wheel for a car, which changes the direction. We have the brake, which slows down. We have the gas that push forward and increases velocity. But actually, it's all of them are accelerators, right? Because we need acceleration to turn, we need acceleration to brake, and we need acceleration to increase the speed. All right. So let's take a look at these two slides to finish the PowerPoint, the theory class. This is non-related to circular motion. This is relative velocity, and it's a fairly simple definition. So when the velocity of a moving object it's seen by a particular observer, it's called relative to that observer, or simply relative velocity. So we would need to define a frame of reference, and that frame of reference, as I always say, it's what it will let you analyze the problem and be able to identify the equations and the signs of the quantities that you're using to solve it. And in this case, the frame of reference will be a coordinate system plus a time scale. And then let's look at this example. So we have a train which is moving. We have a passenger inside of the train, and we have a cyclist outside of the train. So we will have two different different frames of reference. We'll have the cyclist frame of reference and the train frame of reference. So the train frame of reference will be moving at a velocity which is relative to the cyclist. So the cyclist that looks at the passenger will basically see the train, the velocity of the train, and the velocity of the passenger. Right? So we can say that we can define positions of the objects that we're looking with respect of the system of reference that we are using. So let's say we have the position of the passenger. We want to write it, the position of the passenger, with the system of reference of the cyclist. So that would be the position of the passenger in the system of reference of the train, which is B. And then we need to add the position of the train with respect of the cyclist, because it's moving too. That's basically what we have here, right? So we have position of the passenger with respect of the train, and then the position of the train with respect of the cyclist. So for the cyclist, the position of the passenger will be the addition of those two positions. And the same logic we can apply to the velocity, right? So the velocity of the passenger with respect of the cyclist frame on the x-axis would be the sum of the velocity of the passenger with respect of a train and the velocity of the train with respect of the cyclist. It's quite simple. It can be kind of messy if you just hear it, but if you just sit and take a look at the expression, it's very intuitive actually, because of course, if you want to take a look at what's going on with the passenger, which is moving within another thing that it's moving, which is the train, then you gotta take into account the moving of the train, which is done here. And to be more strict, more general, so before we were talking about a straight motion, so to be more general, we can define this in a 3D space, and we can define the position vector now in this case in space. So the position vector will be for the person, the passenger, with respect of the cyclist, would be the sum of the position vector of the passenger with respect of the train, and the position vector of the train with respect of the cyclist. So that's what we have here. And if the train is moving relative to the cyclist, so the train is going forward, then we can rewrite the velocity, now a full vector, with respect of the velocity of the passenger with respect of the observer outside the train. And that is called the Galilean velocity transformation, basically, when you are taking into account the movement of the second system of reference, which is here, YB, XB, and the first one, which is the cyclist, YA, XA, ZA. Well, didn't mention ZB, but that is there. So is there any questions about this? It's kind of can feel confusing because of all the sub indexes, but it's pretty straightforward if you think about it. It's just something moving within something that it's moving. So that's the way you write that position and velocity of the thing that it's moving within the other thing that's moving. All right. Okay. Let's take this last 15 minutes to go through a circular motion problem, so you can have that and we're ready for next week's class. So we can move forward to newtons. Okay. Let's take a look at problem V, which is it's 5, section 5. Problem 3. Section 5, problem 3. We have a circle, which I'm not going to be able to draw nicely, but I'll try. You have a circle there, and radius. And we have some acceleration with an angle. This thing here is 40. The velocity r equals. Okay, so it says a particle is moving around a circle of radius 2 meters as 2 meters. Yeah, that's a typo there. At a given time, at a given instant, a total acceleration of modulus 20 meters per second square in the direction that makes an angle of 40 degrees with the radius as shown in the figure. Yeah, that should be. Oh no, it's okay. It's has. Yeah, yeah. Okay. Has at a given instant a total acceleration of modulus 20. So we know the total acceleration, and we know that it has an angle of 40 degrees with the radius. So that's what we have there. So again, this is a vector. It says give the centripetal acceleration vector at that instant and give the tangential acceleration vector at that instant, and then give an expression of velocity of the velocity vector as a function of time. So in order to do this, we would need to project the acceleration into both axes. So let's just kind of zoom in there. So if we can rewrite, you know, let's call it E tangential, the axis, not the vector, the axis, tangential axis. And we have the radial axis. Radial axis. And then this thing is something like this. And then we can simply project that and get both components, AT and AR. Okay, so this is A here. And we know that's 40 degrees, so we can write AR equal A cosine 40 and AT tangential A sine 40. And that would be 20 meters per second square, right? Yeah. cosine of 40, just do the math for me. So I don't have, well, I have the calculator here. But if you want to do it same time, you can check numbers. 20. And this is 20. Cosine of 40. Cosine 20, that's 15.32. That's 1285. Okay, meters per second square, meters per second square. So we have both components there. So that's basically answering A and answering B. So just to be strict here, is asking for the vector. So the vector would be the vector AR equals the component AR multiplied by the unit vector that we can define here. This would be E, we call it E tangential, so E, and here we call it E normal or radial, it's the same. So E, and this is a T equals A T, the scalar multiplied by the vector E T. That's the strict way to put it. Actually, let's put it this way, because you know the movement, it's going that way. So the best way to define it would be E, to define ET would be pointing the other way. So this would have a minus here. If I would be working with the with other variables here, I would have defined the unity vector for this movement pointing to the same direction of the velocity. So we know that then we have negative acceleration. And I think that's it for this. Oh yeah, give an expression of the velocity. So the velocity we can do Vt equals Vt0 minus At multiplied by t. And that's tangential. And that would be the expression of the velocity. So that's how it changes in this particular time where we have the acceleration pointing down. E, yeah, E, so En and Et is are representing the unity vectors. So they are analogous to I, J, and K. They're just unity vectors, which you can use to define your vectors in the system of reference. So you get the multiplication of the scalar, which is the component of the vector, with the actual vector. It's just the way to transform that scalar component into the vector. And you can find this like N or T or R if you define them with different letters. But I think the book is using en and et, so just want to be consistent with that. But yeah, bear in mind that those are unity vectors that you use to express your vectors in the system. And there was another question here. If it was a uniform, well, this is non-uniform at all, because you can see that we have centripetal acceleration, we have acceleration that's changing the velocity in direction, but we also have a component of acceleration. Let me change colors. A component of acceleration on the tangential axis, which is pointing the opposite way. So the velocity is changing in modulus too. So the speed is changing, and it's changing with this ratio here. So this applies to a non-uniform circular motion. Whenever you have, remember, whenever you have acceleration on the tangential axis, then you have non-uniform circular motion. Okay. Any questions about this problem? I can recommend you take a look at the I think it was the problem 4. That's a nice one. Problem 4 is the following problem, just to get some practice, and then of course you'll go over more problems at the discussions with Kate. Okay, so I think that's all for today. If you don't have any comments, let me stop. Stop this. Stop this. Get back to video here. And as I was saying, if you don't have any comments or any questions, concerns, let's just see each other on Monday. And that would be all for today. Let me stop the recording. Thank you, Nicholas. You two have a great weekend.